Now we are going to work on binary tree inOrder traversal, but this time with a different approach wherein we are going to traverse inOrder by iteration. Previously, we had learned about inOrder traversal by recursion without the help of function. So I'm just going to reduce the window size and we know about the explanations given here. I'm going to reset this function so that we write the inOrder functions separately. Okay, and I want to close this so we are all set for implementing the inOrder traversal. But before we work on the code, we'll have a short visual walkthrough to understand inOrder traversal by iteration. Previously, we had learnt about traversing binary tree by inOrder with recursion, with or without the help of function. The algorithm for traversal of binary tree by inOrder goes something like this. If the root node is null, we simply return. And then we traverse the left subtree, followed by visiting the node, and then traverse the right subtree. This is achieved by recursion with help of stack. Basically, recursion creates a stack frame for every function call that is made recursively, again and again. In this session, we are going to achieve inOrder traversal by iteration, meaning that we are going to call and dump value of the elements in the node without recursion. Here on the left side is the binary tree representation with three elements, and for inOrder traversal by iteration, we make use of stack. We'll take a look into the algorithm right away. I'm going to reduce the size of this algorithm here, move it across, and then pull up the algorithm that we have built for the iteration. So it goes something like this. We'll walk step by step. Set a variable current at row, and we make use of stack just as we did in case of recursion. Until curr is not nil and stack is not empty, we have trouble. The current node is not nil, we keep traversing left and then push that into the stack. And when we hit current node as nil, we pop the top of the stack, send that value to the result slice, and then we traverse. We continue this iteration until again we hit this condition where current is not nil and stack is not. So this is the basic algorithm that we use for iteration in lines with what we did with inOrder traversal by regression. We'll further do a dry run and understand things. Okay. Now I'm going to make use of two variables, per and result, which is res. Initially stack is empty, so I'm going to keep this here. Per is initially set at root, meaning it's going to be at 1. So I'm going to initialize per with 1. Let me put it as 1. So this loop is taken if per is not nil or if stack is not empty. Stack is empty, however, per is not null. It got value 1. So we enter into the inner loop. If the per is not nil, we keep pushing into the stack and traversing left. So we check per is not nil now. So we push it into the. Let me go ahead and push 1 into the stack. Okay. Now car is 1, we traverse left. So left of car now becomes nil. So I'm going to change this to nil. Now we iterate for back and check car is now. So we come here. We pop on top of the stack and set car with that value. So I'm going to take this off and then put it here. So I'm going to append it and then change curve width. So this is the pop dot value. Now stack is back. We are done with updating the curve as well as appending the value to the result. Now traverse right. So one is now at right. Traverse right becomes, so I update curve width. Now is kernel, so I'm going to go into the, let me push go into the stack here. Traverse left, so left of those three. So I'm going to update curve width. Further, again, we check if cur is not null. Cur is not null because it is 3. I push it into the, so let me push element 3 in. I'm going to push 3. Traverse left. Left of 3 is now null. So I'm going to make this. Now cur is null. So I come out of this loop, top from top of the stack. When I pop, I update cur, so that's going to be 3. I perform the top operation and then up to that value. So let me go ahead and append. Now, cur is towards right of 3. Right of 3 is. So I'm going to actually traverse. So when I come back here, cur is now nil, so I don't enter into the slope. But pop out the top of the stack. So top of the stack is 2. So I'm going to update here cur with 2, pop out, and then append the value. So now I'm going to append 2 here. 2 is good. And then I'm done with doing that. Traverse right of, so right cur is now. So I'm going to actually update it. When I come back here, again, is cur equal to nil and the stack is empty. So now we stop the iteration and this gives the inOrder traverse. 1, 3. Now as we jump to the implementation, we have the node definition which holds integer value pointer to the left subtree and a pointer to the right sub. The function signature is like this. It holds an input parameter root which is pointer to the tree node and returns an integer array holding the elements of the tree. So we are now going to have variable declaration. So we are going to need result, hold the results. That's going to be of type integer array. And then we are going to make use of stack. So I'm going to define stack. That's going to be array of tree node. And we're going to have cur. That's going to be pointing to the. So from the algorithm that we had learned just now and dry run also that we learned, we know we need to traverse until cur is not equal to nil or stack is not empty. So traverse the tree until cur not equal to nil and stack is not empty. So I'm going to say cur not equal to nil or stack is not empty. So here if we have to find non-empty stack, we need to find the len of stack and that needs to be greater than 0. So if len of stack is greater than 0, it is not empty. Further, we traverse left if curr is not nil. We keep traversing until curr is not nil. So for curr not equal to nil, we traverse left, traverse. So I'm going to say curr equal to curr not nil. And before we move into the next node on traversal, we push the current node into the stack. So stack equal to append stack with okay. So when we have hit current node at nil, we are out of this loop, and then we pop out the stack. So before we pop the stack, we grab the top of the stack into current node. So let's grab the top of the stack, and that's going to be cur equal to stack top of stack. Top of stack is len of stack minus 1. So let me do that. Len of stack minus 1. And then now we pop. So stack equal to stack everything except the first element. So everything except top of the stack. So top of the stack is again now len of stack minus 1. Once we are done with popping out the element, we now need to update result. So we will update result by appending per.val to result. So result equals to append result comma per dot, and when we are done with this, we traverse right. So cur equal to per dot. The completion of this iteration, when both stack is empty and car equal to nil, we come out of this loop and we are ready to now return the result. So return the inOrder list, inOrder result or list. So we are done with the implementation. Take a look at the test cases. So there are three test cases here. The first one with three elements. So expected result will be something like 1, 3, 2. The second one will be an empty 3. So there's nothing in the in-order result. And then the third one will just have one element. Let's check. So before we run, we can do a quick sanity check. Tells me that this needs to be a slice. So I say rest equal to int of slice like this, or I could even declare a slice like this. Either should work. So if I walk through rest of the code, it looks okay. Good to run. Let me increase the size here. See the results. Okay, all of them are accepted. The case 1 has three elements in order traversal. Case 2 has empty tree and there is nothing in traversal. And case 3 has just one element. Perfect. We'll just walk this over multiple test cases as well as I submit here. But before we submit, I can even try the alternate method for declaring slice. I'll run again. But before I run, I close this result and let me run again. Perfect. Either case of definition for a slice works. And that's what I just want to show you up. Okay, good to submit and see the performance. Perfect. We are done. So far we have been able to implement binary tree in order traversal by iteration. That's it.